Computers don't think in tens, hundreds, or thousands like we do. They speak a language of only two states, on and off, represented by zeros and ones. These are called as bits. But how does a computer use just two digits to represent every number we know, including the negative ones? Let's dive in. A number system which represents numeric values using only two symbols, that is zeros and ones, is called as a binary number system. Before understanding binary number system, we need to look into decimal number system, which we already know. The decimal number system is a positional system. In our standard decimal system, that is base 10, we use 10 digits from 0 to 9. Each column represents a power of 10, increasingly as we move from right to left. So ones column is nothing but 10 raised to power 0. Tens column is nothing but 10 raised to power 1. Hundreds column is nothing but 10 raised to power 2. Thousands column is nothing but 10 raised to power 3. So when you see the number 23, your brain knows that the 2 is in the 10th place and 3 is in the ones place. So you have 2 tens, which is equivalent to 20, and 3 ones, which is equivalent to 3. And when you add 20 plus 3, it makes 23. Simple, right? You also know that a 2 isn't always just a 2. Its value depends on where it sits. That is, position of the number matters. If it sits at the ones column, the value is 2. If it is at tens column, the value is 20. If it is at hundreds column, its value is 200. Right? Binary number system or base 2 number system works the exact same way, but it uses powers of 2 instead of 10. It follows the exact same logic and use only two digits, 0 and 1. Instead of powers of 10, each column, it is also called as bit representer, is a power of 2. That is, instead of ones, tens, hundreds, we have columns for 1, 2, 4, 8, 16, and so on. So ones column is nothing but 2 raised to power 0. 2's column is nothing but 2 raised to power 1. 4's column is nothing but 2 raised to power 2. 8's column is nothing but 2 raised to power 3. To represent a decimal in binary, you simply switch on, that is using 1, or switch off, that is using 0. The bit representers that add up to your target value. So if you want to represent number 13, we just look at the bit representers and ask which ones add up to 13. Or you can imagine having a purse of coins where you have coins of 8, 4, 2 and 1. And we need to pay 13. In this case, we need an 8, a 4 and a 1, which would sum up to 13. By putting a 1 in those boxes and 0 in 2's box, we get 1, 1, 0, 1. So in decimal, it's 10 plus 3. In binary, it is 8 plus 4 plus 1. Different columns? Same logic. So far, we have used 4-bit representation for denoting the binary numbers. We can use 8 bits representation as well. When higher bits are not required to represent a number, these positions are filled with zeros. Now we will also look into how to represent signed numbers. When we talk about signed numbers, that is numbers that can be positive or negative, the leftmost bit is the most important bit in this case. This is called as a sign bit or most significant bit. When most significant bit is 0, it indicates it is a positive number. And when most significant bit is 1, it indicates a negative number. Now we will go through an example where we will represent plus 4 in 4 bits as well as in 8 bits format. In 4 bits, plus 4 will be represented in binary as 1, 0, 0. And to represent it as a positive number, we are going to add a sign bit as 0 to its leftmost position, which is going to make it 0, 1, 0, 0. To represent this in 8 bits format, we simply pad the front bits with more zeros. So we are going to add 4 zeros in the beginning of this number. So which is going to make it 0, 0, 0, 0, 0, 1, 0, 0. Simple, right? But what about minus 4? How to represent minus 4 in binary number system? Modern computers have used a clever method called as 2's complement. You can remember the process with the mnemonic as I plus A1, which you should remember as invert plus add 1. Now let's start how to convert or represent minus 4 in a binary number system. So we need to start with the positive number. So how do we represent positive 4? 0, 1, 0, 0, right? Now apply I plus A1. That is, first step would be invert. Flip every bit. Zeros become ones and ones become zeros. So now we have 1, 0, 1, 1. Now apply the second step, which is A1. That is, add 1. So add 1 to 1, 0, 1, 1. And that is going to give you 1, 1, 0, 0. So in a 4-bit system, 1, 1, 0, 0 is a unique pattern to represent minus 4. Now that we know how computers store these numbers, how do we read them back? It's a 2-step process. First, always look at the most significant bit of the number on the left. When the most significant bit is 0, it is a positive number. And when the most significant bit is 1, the number is negative. So let's look at the positive part. If the first bit is 0, which means the number is positive, you can convert it directly using the bit representers that we have learned earlier. So in this example, where the binary number which is represented as 0, 0, 0, 0, 1, 1, 0, 1. As the most significant bit is 0 here, which makes it a positive number, we just need to add the on bits. So in this case, it's going to be 8, 4, and 1, which gives us value as 13. When the most significant bit is 1, that is when the number is negative, to find its value, we need to use our I plus A1 technique in reverse to unflip the bits. So in this case, where a binary number is represented as 1, 1, 1, 1, 1, 1, 0, 0. As the most significant bit is 1, we know that the number is negative. Let's apply I plus A1. Let's invert the bits. So we get 0, 0, 0, 0, 0, 0, 1, 1. After adding 1, we are going to get 0, 0, 0, 0, 0, 1, 0, 0. Now this results in 4. So the original number which was represented was minus 4. Remember, if it starts with a 1, don't just read the bits directly. Use the I plus A1 technique to find the hidden negative value. You can think of the range of the computer's memory as a bit budget. The number of bits you use determines exactly how many unique patterns you can create. The formula is simple: 2 raised to power n, where n is the number of bits. So in 4-bit system, we have 2 raised to 4, which is equal to 16 unique combinations. Because we use the leftmost bit as a sign bit, we have to split that budget exactly in half for positive numbers and negative numbers. So 8 patterns must start with 0, that is positive, and 8 patterns must start with 1, which would be negative numbers. This is where the range gets interesting. On the positive side, we start counting at 0, that is 0, 0, 0, 0. Because 0 takes one of our 8 positive slots, we only have enough room to go up to plus 7, that is 0, 1, 1, 1. Whereas on the negative side, we don't have a negative 0. We can use all the 8 of those patterns for actual numbers, which allows us to reach till minus 8, that is 1, 0, 0, 0. That's why the 4 bits range comes down to from minus 8 to plus 7. Similarly, we will look at the 8 bits number system. Here, our budget grows to 2 raised to power 8 or 256 unique patterns. Now, if we divide it by 2, we have 128 patterns which starts with 0 and 128 patterns which would start with 1. Just like before, 0 takes one of those positive slots. So our 128 positive patterns cover 0 to 127 and our 128 negative patterns cover from minus 1 to minus 128. Hence, 8 bits number ranges from minus 128 to plus 127. You will notice there is always one more negative number than the positive one. Why? Because in the 2's complement system, 0 is grouped with positive numbers. If we try to represent plus 128 in 128-bit system, the pattern would look like 1, 000 and 4 times 0. But wait, that starts with a 1. So the computer would read it as minus 128. To go any higher than plus 127 or lower than minus 128, you don't just need more math. You need a bigger container, like a 16-bit or 32-bit register, to hold those extra patterns. Because of 2's complement, the computer's ALU doesn't need a separate subtraction unit. To subtract, it just finds the negative version of the number, that is invert plus add 1, and adds it. This saves space and makes your computer faster and hardware more efficient. From positional bit representers to I plus A1 technique, binary number system used in computers is a masterpiece of efficiency. It lets a computer handle everything from bank balances to complex physics with nothing more than zeros and ones. Thanks for watching this video. Please don't forget to subscribe.